Here's the patch. It's designed to show in an artistic fashion combustion science and the material science that we were on board to do. Around the crew one more time, Susan Still, the pilot from Augusta, Georgia. There's Mike, MS2, the flight engineer from Mansfield, Ohio. Janice Voss, payload commander from Rockford, Illinois, that's right. Cleveland, Ohio's representative, Don Thomas. Roger Crouch from Tennessee. Gregland Terrace from Demarest, New Jersey.
So finally, the big day we've been training so hard for has come. And what a beautiful day to go into space aboard Columbia. As we're all getting strapped in, I find that I'm not nervous at all. I'm mentally reviewing procedures and waiting with excitement for when I get to start moving switches in preparation for launch. 6 seconds prior to T0, the 3 main engines ignite and throttle up. When the computers see good engines, the solid rocket boosters ignite. And there's no stopping us now. The vibrations I felt during launch were less than I had anticipated, which was nice. The acceleration off the launch pad was less than I've experienced catapulting off of aircraft carriers. But soon, things got pretty exciting. When I started feeling the G-forces build up, pressing down on my chest, I knew I was accelerating faster than ever before. 0 to 17,500 miles per hour in only 8.5 minutes. Now that's pretty exciting. Now we're over 160 nautical miles from the Earth's surface.
One of the first things we need to do when we get up into orbit, to get into orbit configuration, is open the payload bay doors. The shiny surface on the inside is a radiator, and we use that to get rid of the waste heat. I'm sure most of you know how all that works, but we have to get them open just a few hours, or we have to come back because of all the waste heat that we generate on board. The next major activity for me and the payload team was getting the Space Lab activated. You see Roger coming in on the left there. I'm right behind him. This is our first trip into the Space Lab module after getting up into orbit. You can tell it's early in the flight because the module is still nice and clean. Everything is still packed away. That'll change pretty quick as we get things set up for flight. We have to get all the systems activated, the subsystem computer and the experiment computer, get that up and running so we can get heavily into science. You see Don Thomas here working on the world map computer, and you can also see the Space Lab computer next to him.
What was happening on the ground, at first unknown to us, but shortly made known to us, was that we had a fuel cell 2 problem. Fuel cell 2 had high substack delta volts, which is a technical term for saying that there's the possibility that fuel cell 2 could have a fire. So at the upper right-hand part of the screen, you see the flight control team meeting together, trying to go over our options, figure out what the right thing to do. The mission management team met, and the right thing to do was to come on home. And here you see Chris Hadfield, our Capcom, telling us, come on home on day 4.
And one of the big results of the power down that we did was to shut off all non-critical equipment on board, and one of the first things to go back in the Space Lab module was the lights. And you can see here I'm working with a flashlight in my mouth. That was standard operating procedure for us back there, to look at procedures and see what we were doing, and it made for a most interesting work experience back there.
Before things got quite this interesting, the 32 science teams working in the Payload Operations Control Center at Marshall Space Flight Center had started replanning the scientific experiments, and the red team went to work doing the new PCAP, or the new plan for how the science was going to be carried out. The orbiter crew chipped in. Here you see Susan helping on a Japanese furnace, large isothermal furnace for some of the material science experiments. Greg's doing some combustion here. Oh, that's Don doing material science still on the large isothermal furnace. I apologize for that. He's changing the samples here, going with some of the samples that had shorter run times than what we'd previously anticipated doing. And you can see that he's working from a new PCAP that had just been faxed up that day. This is Greg, sorry.
Combustion was one of the important areas of research on our mission, and what I'm doing here is a soot formation experiment. Soot, of course, is an important airborne pollutant. This is the igniter in the combustion chamber. You'll see the flame, an ethylene air diffusion flame lighting. It's actually upside down here. It's forming soot. Our job at this point was to adjust the flow rate of the fuel in order to eliminate the soot formation and bring it just below the soot point, so the flow rate is being adjusted down. The next image is a laser extinction image of the same flame And this is what the scientists on the ground used to quantify the soot formation rate in this particular flame. Another area of research was droplet combustion. Droplets, of course, are ubiquitous in many combustion-using devices. I'm setting up the experiment here. In the next image, you'll see an actual droplet burn. The droplet is formed in between the center needles, and then it's stretched, released, and then ignited, and then it burns. From the burning rate of the droplet, the scientists can understand the chemical kinetics and the physics of the burning process. The next image is an ultraviolet image intensified, and you can see that the droplet burns all the way to extinction, which is exactly what the investigators wanted to try and see.
I spent a lot of time during our 4 days working on the glove box experiments here, and this is one of the material science one from Northwestern University. We wouldn't have been able to do the great job we did up there without outstanding support here on the ground, both at the Johnson Space Center in Huntsville, Alabama, at the Payload Operations Control Center. And our number one man there working with us was Paul Ronnie, our alternate payload specialist, who did an outstanding job helping us get all the experiments done in time.
We had a couple of experiments on board that were looking at hardware we might be using for the space station. This is an example of how we could upgrade an experiment as the station evolves, as you learn more about the science or improve the hardware to allow you to change experiments over the course of space station's life. This is the combustion module where at the beginning of the flight inserting the experiment mounting structure for the soot flame that Greg was talking about earlier. Halfway through the flight we'll change these out and put in a flame ball experiment that would be the second half of that combustion experiment.
The very first full day on orbit, one of our first jobs was to activate some protein crystal growth experiments, and that's what Dawn and I are doing here. Protein crystals, of course, help the scientists on the ground understand the structure of the proteins for which they can then design drugs. Our job was to photograph with 35mm photography the activation process.
One of the major challenges facing a seven-person crew like we had is to convert the ascent rocket into an orbiting laboratory. And basically, you're trying to stow away about 10 pounds of potatoes in a 5-pound sack and then deploy all the various experiments. This is Janice taking an air sample in the lab, one of the tasks we do when we first activate the lab. And then here you see me working on the computer, and I'm completely upside down on the ceiling, and that's one of the things that we did a lot of, is to try to spread the people out. 7 people on the middeck don't fit very well on the floor. Of course, we have to get exercise, and there's Jim doing the ergometer. Our exercise periods were compressed because of the short flight, but normally this is a very important part of our day.
As you might imagine, the view out the window was pretty impressive. This is the Baja Peninsula, which is oriented kind of upside down. The United States is towards the bottom of the screen, with Mexico up in the upper left-hand corner. This is part of the Middle East, with the Nile River in the top portion of the screen, the Red Sea in the middle, and Saudi Arabia towards the bottom. It's one of the prettiest parts of the world, I think. This is Sinai Peninsula in the same area with the Gulfs of Suez and Aqaba. You can see the Suez Canal up in the upper left. These pivot point irrigation circles are all over the deserts, especially in the Middle East. They go down thousands of feet to bring up water for irrigation.
One of the most spectacular sights we got to see from our short mission was Comet Hale-Bopp. And what you're looking at is a sequence of pictures here, watching the comet actually set through the atmosphere, and we're actually able to see it set beyond the limit of the Earth here. You can see also the orange lights there that are down on the Earth. Those are fires burning over Central Africa as we passed over there. The sunsets are spectacular, although they're very short and they occur over like 10 seconds or so. We get to see about 16 of them every day, which makes up for their shortness.
Well, after a lot of unexpected quick work, we had the vehicle in shape, ready to come home. Here we are on deorbit day. Everybody's suited up. Susan left, flight engineer Mike there in the middle, and me on the right. We did the deorbit burn, made a safe and successful fuel cell entry back into the Earth's atmosphere. And at about this point, at about Mach 0.9 is where I had the opportunity to fly the space shuttle for the first time. I had about 1,000 practice shuttle training aircraft approaches, but I had never, as pilot, had the opportunity to actually fly the shuttle. And when I first took control of the vehicle manually, I did a little pitch pulse to see how it flew, a little roll pulse, and I told Susan, hey, it's just like the STA. And I think that's a tribute to our training people and system that a first-time flyer can feel that comfortable. Here we are rolling out on final approach. Don got a good view of the runway out over Susan's shoulder. At 2,000 feet, I did the pre-flare, and at 300 feet, Susan dropped the gear down. Right here, we had a little bit of crosswind from my right to left as I was looking out the commander's window. That was causing some concern by the people on the ground, and you see that I did have to make a little correction back to the center line to the left here, and then stop the rate by dipping the right wing down to have a 0 cross the runway rate as we touched down. The vehicle touched down. The whole landing task was well practiced in the shuttle training aircraft, and I felt comfortable with it. As I lowered the nose, Susan put the chute out, and the chute causes a lot of drag, or at least it seems that way after several days of zero gravity. The jerk that you get seems like a lot, and you just have no desire to really put on the brakes. You let the vehicle roll out with almost no braking. Susan drops the chute at 60 knots, and I do use the brakes here for about the first time to bring it to a full and complete stop. I found the brakes, they weren't draggy. I did find the nose wheel steering to be fairly stiff in the sense that it reacted very quickly to any inputs that I made.